Okay, hi everyone. Welcome to another stream. Today we continue with the post that we started writing the last time. Just as a reminder, basically the idea was that there were three types of parallelism that we could use, and the idea is that we go over all of them and then describe what to use for what reason. We also talked about like three rules of thumb that we have to have in mind. We want to use each of these methods. Okay. And today I will continue a little bit with writing it, and hopefully I can finish it, because I'm also excited to create another video just putting everything together. Let me kind of want to make it all in single quotes. Let's see. Okay, looks good. Yeah, and then we had we talked a lot about the issue of these concepts. Let me also. So also we talked about all of these concepts. I probably will also go over them more throughout the this stream. So for the types of parallelism, I would like to say there are three main types of maybe at least when it comes to serving LLM on GPUs. Okay, the first one, the pipeline parallel. I want to one second. There was also one paper that we saw last time. I mainly want to get some screenshots. I think I also already taken some, but yep. So basically I will just break this into 3 parts. This one would be pipeline. This one would be data, okay, this one would be data. The other one would be tensor. Okay, so I don't have a laptop. Okay, thanks Jay for popping up and saying hi. I hope everything is going good with you, and yeah, hopefully next week I can see you again. Like, but yeah, it was really nice hearing back from you. Okay, take care. Okay, and so I think I have to just upload the upload the files here. Go here, and then how can I reference it? Okay, so basically each type basically the type that you choose I mean, sometimes there are some dictation things that I double guess it, and it feels some words that feel strange to type. Anyway, basically the type that you choose dictates how your model it may take 1 month to get back. Okay, in any case, I wish you all the best. Also have a good night. Alright, take care. The type that you choose dictates how your model is distributed among your GPUs. And then first would be will hopefully give you good about the concept. Also this paper and okay, just say that take the pipeline, that PNG, pipeline parallelism figure, and this approach breaks, like splits the model into by its layers, and each will live on different GPUs. For example, if you have a like neural network, or like any other model in a sense, for example, if a neural network with let's say 30 layers, this approach to if you have a neural network with 30 layers and 20 layers and 4 GPUs, this approach will put layers 1 to 5 on GPU number 1, layers 6 to 10 on GPU number 2, and so on. And I think I'll also put the image in the last part. The images. Okay. What else? We have pipeline bubbles. I think I also had some pictures related to that. Okay, this is the just copy this and let me go to Paint. This would be GPU utilization pipeline. I think the last part would be a bit confusing, to be honest. So this is the what you're seeing here is basically the GPU utilization on 4 GPUs when I was using in pipeline parallel, and as you can see, the utilization is terrible. But then the important thing is that here around the 1 hour mark, I stopped the generation and then started again. So I'm thinking to just cut it from the 1 hour mark, and then we can, I think it would be more clear. Also, maybe I can find the job they submitted again, and then I can get a better picture. 1 second. Okay, I got it. Let's say I'm interested in this, and I only want the starting point until here. I wish I kinda could export some of this stuff. Yeah, let me see. Okay, and then I think this is a better picture. And then you also have to place it. Okay, I think this is more clear, I would say. And then also write about pipeline in action. I was running, I'm not sure which model it was, but probably I can also maybe put this on top. Okay, never mind. I was running llama blah 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 on for A40 NVIDIA GPUs using Parallelism. But the utilization was way off than what I was expecting, and the reason was that I was simply using the wrong approach. Below is a figure that shows the utilization of the GPUs during the the data generation. Hi, model parallelism. Do you also work with these topics? Okay, and then the picture, and then the picture would be come after. To be honest, there is no source code, but what do you mean? Do you mean to share the blog post on GitHub or what? Yes, I already... Okay, let me double check. This is the GitHub, and also, of course, you can just read through the material. This is also the link to the blog website. So at the moment, the current post is on draft, but I also already had another post related to installing axolotl on HPC, so maybe you're interested. You can also have a look. I also usually make the, I mean, at least I did it for the last blog post. I also made the YouTube video about the blog post, so you can also probably find it on my channel. Link address, and this is also for the last one if you're interested. Yeah, no problem. Also, welcome to the stream again. And may I ask, what's your, like, are you also interested in the topic, or do you also work with this, or what's your interest in general? Yeah, I will definitely add it. But at the moment I'm writing it, and probably after the writing session, after the stream, I will also push it to GitHub. I mean, actually I can also just push it now just to see if the images that I added also render or not. And updates, parallelism, post. Yeah, no problem. Yeah. Okay, where were we? Also for the, so this is the whole idea, the pipeline parallelism that I used, and now I also add the image. I'm also learning all these things. Yeah, sounds good. But for me, it's, I think it just clicked when I went over this pain, or like not pain, but trying to figure out what happened, that I went from this to something more like, one second, let me show you. It was also really interesting. I went from I went from the image on the left to the one on the right just by changing some parallelism approach. So for me it was also really, I mean, satisfying, and also really good to see it in action, because so far I've been really kind of struggling with it, especially when I was reading VLLM documentation. Every now and then this topic of parallelism did not really click for me, but I also hope that this would help if you're also learning these topics. And yeah, it's really an interesting topic in general. Do you also use any HPC systems, maybe for research and stuff, for your university, or not? I mean, do you have access to such systems? Because the resources that I use is mainly for our university, and I was just curious, like, if you also use anything similar. Also, I will share this if you are interested. Let's see. Okay, so I still have the image could not be loaded. Okay, because it's, I think then the PNG should be JPEG. Okay. What else? And then I also want copy. Also copy the name. There's a figure shows the utilization of the GPUs during the inference. Okay. And then for the tensor parallelism, I would say I think I will also take this and put it here. So I will first go over the different types and then I will talk about the personal experience. Okay, tensor parallelism. Here, like above, we just say this approach splits the matrices and puts them on different GPUs. So basically, each GPU will hold one part of the each layer. So also our example, for example, if you have a neural network with 20 layers and 4 GPUs, very simplified. Yeah. If you have a neural network, 20 layers of 2x2 matrices and 4 GPUs, the first element of each, or should I say the element at 0 and 0 of each layer will sit in GPU number 1. The element at 0 and 1 GPU number 2, and so on. And then I add This was data. This was this is tensor. Parallelism and tensor would be tensor parallelism figure. Okay. I could also, I think it's better if I keep the examples with 3 GPUs, because on the images we also have only 3 with, let's say, 30 layers and 3 GPU. This approach will put layers 0 to 9 on GPU number 1, layers 10 to 19 on GPU number 2, and so on. And if you have a neural network with 30 I think the example would be a bit hard here. I think I'm gonna stick with the okay. If you have 30 layers of 2x2 matrices and say 3 GPUs, the element of 0 officially will be set on GPU1, and the element of 0 and 1 and 1 and 1 each layer will sit on GPU number 3. Okay. Data parallelism. I also wanted to talk about this I think I cleared it. Yeah, so also one important concept is the pipeline bubbles. When you put each layer on a different GPU. So if you put each layer on a different GPU throughout the process, throughout the computations, one layer should wait for the last layer to finish its calculations and pass the data. This adds a bit of adds small pauses during the computations from GPU to GPU, and this is something known as pipeline bubbles. So basically you just pass the data to your first layer, but then your first layer is sitting on GPU number 1, and then it has to, so GPU number 2 doesn't have any data, it waits for GPU number 1 to finish. So this small pause will kind of I think increase a little bit, and then this will be like a bubble. Basically your pipeline is not fully utilized. You have these gaps in your GPU, which is kind of going to waste, and your GPU would not be fully utilized. So that's the idea. One really important concept that is that when you put each layer on a different GPU, the computation, one layer should wait for the last layer to finish calculations and pass the data to the next one. It sets a small pauses during the computation from GPU to GPU, and is sometimes called pipeline bubbles. Okay, and then tensor parallelism, and now data parallelism, and also we'll talk about load balancer. LLM data parallel. I think we saw it last time regarding the internal load balancing of LLM. VLLM comes with an internal load balancer for you to use. Balancer to use when it comes with an internal load balancer to expose single API endpoints when you are using data parallelism. Okay, also I put this internal load balancer into, oops, and then I sent a link. And you're using data parallelism. Okay. If all of your GPUs are holding one replica of the entire model, the question would be who should handle the next incoming request. This is something that is handled by a load balancer. The criteria on which the decides how to route the incoming request can be different based on the can be things like, I think, round robin, balancer strategies. Yeah, there's round robin, performance aware, like server capacity, constant routing for the API. Round robin, and also there's this performance aware, like load aware. Load aware. And more. That has less Okay. Usually in general, if you have a GPU and everything fits on that, you are like good to go only having that GPU, because you can fit everything on that GPU and everything would be fine. But if you are looking for more throughput, then you kind of want to add this replication, so that you basically have more GPUs and then you can just serve more requests. So that's when the data parallelism comes in. But yeah, data parallelism, the entire model sits on a single GPU, and there would be no hardware restrictions, but you probably only want to increase your throughput. For example, if you have an let's say, I don't know, 20 billion parameter model, like 10 billion parameter model, yes, but 7 billion parameter model, and if you have a model that fits on one GPU, but you have 3 available GPUs, you can just use all 3 with data parallelism to like multiply your throughput by a factor of 3. This is the best case. The entire model sits on a single GPU, and it is exactly copied among the other GPUs. So this approach just replicates the model among the available hardware. But probably only want to increase your throughput. You might consider this approach when there are no hardware restrictions to fit the model. But you probably only want to increase your throughput. For example, if you have a model that fits on your GPU, but that fits on one GPU, but you have 3 available GPUs, you can just use all 3 with data parallelism to multiply your throughput by a factor of 3. So basically, you just also in the picture, where was it? So basically the entire model sits on your different GPUs, and basically if you just say so this, let's say, gives you 10 request throughput, and then for example if you add another one you get to 20, and then the third one will get you to 30. So it's like one GPU is kind of enough to serve you, or like to give you some work. I mean, the problem with the other type of parallelism was that you couldn't even fit the model into one single GPU, so then you had to go and take other measurements. But here the thing is that you can basically get some work done anyway, but you want more throughput, and this is when you use data parallelism. This approach is a bit different than the other two because can you also share your LinkedIn URL? Yes. And okay, let me put this maybe on the very top, or okay, this approach is a bit different than the other two because for pipeline and data parallelism, you cannot get any work done since, can you put it this way, for pipeline parallel and data parallelism you cannot get, and tensor, sorry, you cannot get any work done since your model does not fit on one GPU. So you use more hardware just to be able to use the model, but in data parallelism use more hardware to increase the throughput. Use more you replicate the model and use more hardware to increase the throughput. Okay, so yeah, that's the whole idea, I would say. No problem. That's a whole idea, and yeah, for me the data parallelism is a bit different. And as I said, you basically can just get around generating some data or like answering some requests with only one GPU, but you add more layers to just increase the throughput in general. So for me, that's maybe a bit, I don't know, maybe I'm thinking about it wrong, but at the moment it kind of sounds to me a little bit different than the other ones. The model is the one, this approach just replace the model. Okay, and then I also add the image here. And then this would be the data. Oops. Okay. Update. Okay. And now the personal experience. Here I talk about what the use case was. In my case, I wanted to generate 4,000 data entries, basically just some questions, and compare them to the goal in the end would be to compare them to GPT-OSS, like the answers from GPT-OSS and the answers from GPT-OSS would kind of serve as a golden answer. So the idea was to kind of compare. And I also didn't just want to, of course, you can't really compare a 3 billion parameter model to 120, but I also wanted to do some fine tuning on the Llama 3B. So maybe the answers would kind of improve and it would be like sound really, really good if you could, for example, get to almost the same accuracy or like same performance if you could just fine tune 3 billion parameter model and get it close to what GPT-OSS is performing. So that was the idea, and I kind of needed to just generate this data, and I had to just serve the model and just to create this data set from the Llama 3B. Pipeline parallelism in action, and then I talk about the running the model on 40 NVIDIA GPUs using pipeline parallelism, but the utilization was way off. The reason was that I simply using the wrong parallelism approach. So again, this is the thing that I showed here. This one was really bad. The utilization was not there, and I tried just tensor parallelism and then it just worked. And yeah. So later on, okay, now for the so I changed the change the approach, and I got this would be the tensor utilization. Also, we upload it. I changed the parallelism approach. I mean, I wrote so many times. I wrote 28 times the word parallelism. I changed parallelism approach from pipeline to tensor parallelism, and the GPU utilization went up to almost up to 90% and stayed there. So, and then I also add the image. With tensor, also the image would be this. Okay. What else? Okay, I changed the approach, and then it was fully utilized, and what else? I should have one thing I realized when I was writing this blog post is that I should have used data parallelism instead of tensor parallel, since the model would perfectly fit. The model would be perfectly fit on one GPU. Tensor parallelism has overhead of breaking and combining the calculation between 4 GPUs. I mean, I'm not really sure about this, but let's check it. Tensor parallel overhead. Okay, it says that increasing tensor parallel size beyond what is needed can actually reduce performance due to increased GPU communication overhead. Let's say, just say GPU, GPU communication, as overhead, as GPU communication overhead, and I could simply just increase 4x the throughput by using a data parallelism approach. Within this scenario, sets tensor parallelism 8, parallelism 2. Okay. Let's walk through one example. So the example is just to give some concrete idea. For example, we say, let's say you set tensor parallel size to 8 and pipeline to 8 and parallel to 2. And you are using 2 nodes, each with 8 GPUs. So I mean, there's also this question that which one is applied first. Also, let me check the example. So there's also this question like, would first the let me put it this way, question, would first the tensor parallelism be applied and then pipeline? So basically you're kind of breaking your model. Yeah, you're breaking it. You're saying that I want to use tensor parallel size 8 and pipeline parallel 2. So let me also bring the picture here. Yeah, so so you're using the I think I also had another picture, 1 second. Let me check something really quick. Because I also want to put it. Okay, I think I have to edit some pictures. With paint. And then I also would like to delete this. This would be data parallelism. And then this would be tensor and then this would be pipeline parallelism. Okay, and then the pictures again have to upload it, name it all 3 types. Yeah, so basically you are breaking the model both from the layers, which is pipeline parallelism, and also tensor parallelism, like with you breaking the matrices and the model, the layers. So the question is, do you first break the layers and you put these layers onto separate nodes and then break the matrices for each of those sets of layers within the node, or do you kind of break the matrices first? So I don't know if I could explain it properly, but I think this would be a question, and I believe that first the pipeline parallelism is done. You can also double check. First pipeline. Okay, I will write something that I have to double check this. Okay, okay, let's do it now. When using both pipeline and tensor which when combining pipeline parallelism and tensor parallelism on multiple nodes, tensor parallelism is typically applied first within a node, followed by pipeline parallelism across nodes. Using slower network, I think I'm not sure if I can find a good picture. What is this? Okay, let's keep looking. I mean, they don't talk about okay, what is this? Model parallel intro. Oh boy. Sample model with 4 layers. Micro batches, did it get through? Okay, this micro batch is also a question for me. I think I also have to have a look at that. Here. Pipeline parallel. I'm not sure if it's visible or not. Okay, much further. So pipeline parallel, tensor parallel degree 2. I mean, this is pipeline parallel degree 1. So you can see that there's also this DP group, I think data parallel, so you can see there's replication. But my problem is talk about mini batch. Okay, let me yes. Hey, let's ask GPT. So tensor parallelism is applied first inside each pipeline stage. Pipeline parallelism is applied on top of that across stages. So yeah, it says that the model pipeline stage 0 tensor parallel group. Okay, visualization. Stage 0. Pipeline stage. Pipeline stage 0, 1, 2, 3. And then okay, what's next? Each key represents a GPU, each color represents the node. Okay, this is, let me, okay. This would be multi-node, and then in my blog post I will here and copy this. The path would be, of course, this one. Multi-node, parallelism, image source. Oops. Okay. First we break the model layer layer one. I'm not sure if it's like a right term. Layer wise, we put each layer set. We put, let's say, sublayers on each node, and within that node we break the tensors among the available GPUs. So for example, okay, let me do the example here. For example, if you have a model with 30 layers and 32 layers, and you will take the first 8 layers and put it on node 1, and the second 8 layers will sit on node 2. The first 8 layers will be distributed via tensor parallel approach among all the available GPUs on that node. Okay. The status, I think also again the same stuff. Then push. Okay. I think we wrote pretty much, to be honest. We wrote pretty much. All right. Yeah, to be honest, this stream was a bit more typing and less talking. I think last stream was more insightful in a sense, but we kind of figured out most of the things last stream, and then this time we just yeah, we had to kind of just write it down, you know. But in any case, I hope that also let me goes up to right. Okay. Content posts. I'm kind of curious how the I hope the images would load. Okay. So pipeline parallel, tensor parallelism, data parallelism, and looking good. I think it should still be updated. I mean, this is the last version still, I guess. But good that the images are loading. This looks a bit strange, the quote here. Maybe if I put it like... Can I put a dash maybe? I think I want these lists within lists. Tables, quotes, inline HTML. Line break. Oh wow, I could also add the YouTube video. They can't be added, but you can add the image with the link. But losing the image sizing and border. Okay, this can be interesting. Then I also sent the ID here. I'm not sure if the ID means okay. So this one, so with the ID, to ID. Okay, let's see. Site. Add YouTube video link to axolotl post. Then pushing it. Then okay. The sad part is that I don't have a I wanted to also have the image source like a caption or something. Parallelism. Take the image below from this blog post. And okay. Oh wow, this is actually a good blog post. Crazy. Nice. The last post 2024. Okay. Okay, that's it. And I will write about the lessons learned later. But for now, okay. So at the moment, I think there was a good progress. I'm happy if I leave things here. It's almost done, to be honest. And yeah, I think the second blog post is done. And I just pushed everything, right? Yeah. Update, parallelism post, and then push. Okay, so all done here so far. I think next time I will just go do the final polishing of the blog post. And later I will also create a YouTube video. So thank you for joining, and I hope the discussions were helpful. Next time, I'm not sure, but maybe next time I do a bit of like a different type of a stream. I have a couple of things in mind, but yeah, we'll see. But in any case, if you if you attended, thank you so much. Have a good day, have a good night, and I hopefully see you again on the next one. Take care, bye bye.